Very happy to have Matt here and telling us about quantum mechanics in directionless time. So please, take it away, Matt.
Well, thanks very much for inviting me to what looks like a great conference. And I'm very sorry and very kind of gutted not to be there in person. Now, I should say a little bit about myself. So I'm not a physicist, but I'm a philosopher that's worked, in and around kind of physics departments quite a lot. And I thought I would use this opportunity to kind of, put forward some of my philosophical views about time and see how they relate to some issues in quantum mechanics where people have motivated like time symmetric accounts and things like that, and see how it relates to this idea of a fundamental arrow of time. So the aims are quite broad, and I'm going to try and cover a lot of topics and raise lots of issues for discussion later. But my aim kind of going into this, so firstly, what does quantum mechanics tell us about the metaphysics of time? Right, metaphysics of time has, rightly or wrongly, become a bit of an autonomous subject in philosophy, and I'm one of those people that thinks that it should not be at all divorced from physics or psychology and so on. And it's interesting to learn, what particular things do we learn from quantum mechanics about the arrow of time, which are over and above things you get from classical mechanics or statistical mechanics and so on. Importantly, does quantum mechanics in any sense imply that there's some sort of fundamental arrow or direction of time? And what do kind of the various time symmetric approaches to quantum mechanics say about the metaphysics of time, and how should they be interpreted? And are they open to kind of different types of metaphysical interpretation? So the way I'm going to go through this is, in the first part, I'll just take you through some sort of the kind of conceptual way in which I think about these things. It's become quite kind of a canonical way to think in the philosophy of time, maybe less so in physics. And then in the second part, I will talk through the position that I've defended, which is called directionless time, or the C theory of time, what it means for time to kind of fundamentally lack a direction. Then I'll look at a couple of arguments that have been used by some to suggest that there is something like a quantum arrow of time, and how that fits with the kind of the philosophical picture that I would have defended in part 2. And then in the final section, I'll just touch on a couple of different ways to go about time symmetric quantum mechanics and extract what lessons we can get from those for the philosophy of time. So there's a couple of general questions we can ask about time. Now, if you look up at any introductory textbook on the philosophy of time, the central question you'll see that's kind of dominated discussion, certainly in the last century, but arguably even since the pre-Socratics, is this question of does time flow? And this idea that we're meant to have kind of an intuitive feel of what it means for time to flow. This is something which has historically divided the A theory of time from the B theory of time. Now, I defend a third theory which is kind of similar to the B theory in some respects, called the C theory. And both the B and C theories say that in some sense time doesn't really flow. There's a sense in which the flow of time is some sort of cognitive artifact, or it's a projection, or it's an illusion, or something like that, but it's not something that needs to be written into the fundamental equations of physics. Whereas the A theory of time holds that there's something really kind of fundamental about the flow of time, the passage of time. This is independent of us, it's not just our preferred way to describe time. And there's a second question, which is sort of independent of that, and that's the question of whether time has some fundamental direction. Now, historically, that's been tied up with the idea of whether time really flows. But for various reasons I won't go into in too much detail, the question of time flow has raised so many independent logical paradoxes that you can kind of put to one side while still focusing on the question of whether time has a preferred direction. And it's this question of whether time has a preferred direction that I think has a lot more relevance to a lot of foundational questions in physics, such as concerning the thermodynamic arrow of time, and also issues concerning the quantum mechanical arrow of time. And my preferred theory is what I call the C theory of time, which holds that time is fundamentally directionless, whereas the A and B theories, although they disagree over whether time flows, they both hold that there's some sort of fundamental directionality to time. Now, these debates, at least as they're commonly phrased in terms of A, B, and C, go back to this unflatteringly depicted Cambridge philosopher here, John McTaggart. And McTaggart had a famous paper. It's very, it's borderline unreadable now, but it was a very popular paper at the time, and it's forged this way of talking about time, which has become very commonplace across philosophy and the sciences. So he thought that there's different ways in which we ordinarily represent time. We can think of time in terms of what's past, present, and future, right? That's something that changes over time, right? This conference was future, it's currently present, it will be past. So if we want to keep writing down the A series of time, we have to keep updating it. It's effectively many different A series over time. Or we could order time in terms of earlier and later, right? So the writing of this talk was earlier than the presentation of this talk, and the relief felt after this talk is finished is later than the talk itself, and so on. And these are not facts that actually change over time, unlike the A series. And this third series, which is much less talked about, called the C series, is this idea that time is also ordered in terms of like a symmetrical betweenness relation, right? This talk that I'm giving now is located in time between the preparation of the time of the talk and the relief felt after the end of the talk. So we can think of time also in this kind of very symmetrical way. McTaggart says that the C series, it determines the order of things in time, but it doesn't determine a preferred direction. Right, so it's common to see these kind of pictures, these graphical ways of representing these different philosophies of time. So on the left, here we have this idea that there's a preferred present moment, and that tells us where the moon is relative to the Earth right now, and we can see that projecting into the past, right, the relative position of the moon and the Earth changes, and projecting into the future again, it changes. Over time, we have this kind of corkscrew of the moon around the Earth. But on the A theory, we think, well, there's really a fact about where the moon is now, and that moment is special, right? There are facts about the past, there might not be facts about the future, but the future will become real, and so on. Whereas on kind of the block universe associated with the B theory of time, we think that there's nothing inherently special about what we call the present moment, right? It's special to us because that's where we're located, but it's not like some sort of further cosmic property of the time which is simultaneous with us, right? All times past through future are effectively equally real, and we live in this kind of four-dimensional universe. Now, the debate about the C theory of time is just a debate between two different interpretations of this block universe, right? Does the block universe have an initial end and a final end? Does it have a preferred direction along which the laws of physics apply? Or is it this kind of undirected block? Right? There's no real fact about which is the earliest and which is the latest. This is something that we can sort of build in as a kind of higher level facts. And that's the view that I've kind of defended in my own work. And I think that there's various merits of this view. The main kind of deficiencies come through the counterintuitiveness, perhaps, of thinking of time in this way. So we can think of these three broadly different theories of time, A theory, B theory, and C theory, in terms of like a descending structure which is attributed to time. Right? On the A theory, time is really dynamic, it's really directed, and it has this basic ordering of times. On the B theory, it lacks this dynamic property. Time is effectively static, but it still has a preferred direction. And on the C theory, we give up both the kind of the dynamic property and the directed property, which is have this kind of bare, symmetrical ordering of things in time. So we have this idea that the C theory is kind of inherently a simpler way of doing things, but it can kind of clash with common sense and potentially clash with some explanations that are given within physics. We'll see why that might be problematic, and that might actually be a good thing in some cases. Now, the way the arguments usually go is that, well, we have some sort of, appeal to our experience, our common sense intuitions about time, which prefer, which kind of put some preference on the A theory. And we see this not just coming from armchair philosophers, but also physicists who might just in that moment be in the armchair. People like Arthur Eddington, Paul Davies, and many others have sympathy for this view that time really does flow, really does pass. This is something which the fundamental laws of physics seem to neglect, and it's something maybe we need to try to write back into the laws of physics. This is a view I find kind of unappealing, but also just not well motivated in the first place, right? The thing that ultimately is beneficial for the A theory is that it reflects our common attitudes towards time. We supposedly see or feel like time really flows or passes. The present is more real than the future. And we think of there being facts about the past, whereas there are things we don't know about the future that are, in a sense, open to us. And we might want to write down this way in which we interact with time in terms of a model which looks like the A theory, that doesn't provide evidence that time is really like that. Right? And we certainly would think that when we get to fundamental physics, there's going to be all sorts of ways in which the world is represented which don't directly correspond to the way in which we experience things. And we shouldn't put too big a privilege on our experience. And that's been one of the main reasons why people have preferred the B theory over the A theory, because it doesn't try to put in the preferred present moment and the flow of time as genuine features of time independently of us. Right? We don't think that these attitudes that we have to correspond to the so-called ontology of time, the kind of the actual nature of time. And it's been widely argued by many, including people like Einstein and Kurt Gödel and various others that made explicit arguments to this effect, that the ontology of something like the B theory better fits with the time of physics. The obvious case in point is that when we're dealing with the relativity of simultaneity in relativity theory, it becomes seemingly a little bit anti-physical to try to write in some sort of three-dimensional preferred present moment when the physics doesn't really naturally support that. So not having to define a present moment is kind of something in favour of the block universe. We don't have to think that there is a correct way to slice up this block into three-dimensional slices. But there are various kind of analogous intuitions that are often used in favour of the idea that time just has a preferred direction, that the block universe is a preferred direction. Well, we might think that, well, really, processes that we see that we're trying to describe and explain using microphysical theories do nonetheless kind of start out at some state and evolve to some later state. They really go from earlier to later. And frequently still we appeal to the notion of causation, of causal models, and we have this distinction between cause and effect, whereas causes are, generally speaking, earlier than their effects in time. So we have, again, this reason to prefer a model where it kind of has a fact about what times are earlier than others. So we have this kind of B-theoretic structure in such models. So the C theory kind of ultimately does the same thing to the directed block as the directed block did to the dynamic block, saying that a lot of these intuitions don't have to be grounded in the ontology of time. They don't have to be guides to the way time really is, independently of us. But this kind of B-theoretic directed model could just be a useful heuristic for representing certain preferences we have for thinking about time. But in reality, events could really be ordered just in terms of this kind of symmetrical betweenness relation, right? And there's been various arguments to the effect that directionless time better fits with the time symmetry of classical mechanics and the fact that the kinds of arrows of time which we interact with in the everyday world are largely statistical, emergent in nature, not features of the fundamental physics. And we'll look at that in a bit more detail. So thinking about this broad difference between A, B, and C theories, we've never first looked at how they might be relevant to the issue of quantum mechanics. So on the A theory, we might say, well, this models time as having a genuinely open future. So, we can think that fits well with the indeterminism of quantum mechanics. Right, there is a fact about what a particular spin measurement outcome will be in 2 minutes' time. And likewise, it kind of corresponds to this idea of the wave function as genuinely evolving towards the future, kind of making the future come into being. These are kind of a-theoretic attitudes. For the B theory, we can have this kind of more static but directed way of thinking about things and think, well, maybe what fits with the B theory is the idea that the quantum state is just determined by past measurements and not by future measurements, right? It rules out the idea that there's a non-trivial dependence of the present state on facts about the future, right? This can kind of fit with the conventional idea that the Born rule only applies towards the future, and kind of in a sense, time evolution only really goes one way. So one thing that the C theory would in principle do is to open the door to things like forwards and backwards evolving wave functions, which you see in, say, the two-state vector formalism of quantum mechanics, and also allows for, say, non-standard causal pathways when we're dealing with things like Bell experiments. So the idea of retrocausal explanations of non-locality, like we see in like Hugh Price's retrocausal interpretation of quantum mechanics. So, as I say, there are these kind of canonical arguments, and I think a lot of them are not particularly great, but it's worth putting out there just to kind of, lay in the background. The main arguments usually given in favour of the A theory are experience, right? Now, we don't think just pure experience, this is an experience of looking at measurement outcomes, but just general interaction with the world, with our senses. We don't generally think that that's the best way to tell us deep facts about the world, right? And there's this second argument that's sometimes given in favour of the A theory, that it's just hard to imagine how there could be anything like the sort of animation we see in the world without time really passing. But that's sort of, again, it's a rather weak argument. For the B theory, sometimes you see things like, well, causation seems to be something very, very crucial to how the world works, and causes always precede their effects. We always explain things in terms of their past and not their future. Well, that's something that becomes quite interesting in quantum mechanics, where there does seem to be ways in which we can understand the state of a system as depending non-trivially on facts about its future. And also B theorists often appeal to things like the fact that we know more about the past and the future to suggest that there is a sort of basic hour of time. Now, the main arguments that are generally given in favour of the C theory are that things like the passage of time and the direction of time they don't seem to be necessary. It doesn't seem to be necessary to put them into the basic facts about the world in order to explain what we want to explain. And a model with neither of these two features would seem to be simpler. And of course, there are various time symmetries of physics which seem to motivate kind of a directionless world, which we'll get into now. So I think I'm about 20 minutes in, so I'll get to part 2 now. There are various different motivations that have been given in different areas of physics for thinking about time as directionless, and this has been one of my main motivations for kind of setting out this directionless philosophy of time. So firstly is the idea that the kind of reasons in which we normally think of time as being directed are kind of non-fundamental in nature. They're kind of emergent or statistical features of the world. Secondly, there's been many appeals to, say, the time symmetry of classical physics, and also the time symmetry of quantum physics, to motivate the idea that really time kind of is inherently symmetrical. We shouldn't add some sort of further direction if it's not coming out of some basic asymmetry in the fundamental microphysics. And thirdly, there's this fact that the kind of dynamical laws of nature that we get from physical theories, kind of partial differential equations and things like that, don't simply apply from past to future, but they have this sense in which the past and future sort of both depend upon things in the present and the various, kind of the way the laws are formulated. We'll look through each of these in turn to see why there might be kind of this widespread motivation for a directionless picture of time. So I just want you to kind of quickly look at a couple of videos to kind of get a point across, which is more complicated if I were to use words. Right. That's the first mini crash of the computer. Let's try this one again. So you see with this kind of video, right, that it would be very useful to have this skill. I'm going to make it fairly quickly that this is not a video being played from past to future, right? This is a video which is being played backwards. Right? It's representing certain things in the world in the unconventional future to past direction. Right? We can't violate the second law of thermodynamics and just kind of make paper magically go back together just using our fingers in that way. But what comes across when we watch that kind of video played backwards in time is that we have this clear intuition that it is a video being played backwards in time, right? That really time goes the other way, and that's because we have access to certain, apparently irreversible processes that just mark out the preferred direction of time. Right? There's nothing remarkable about this. This is just something that we ordinarily do. When we look at this second kind of video, and I were to ask you whether this video is being played, forwards or backwards in time, it's much more difficult to do so because the video doesn't obviously encode any irreversible processes. Now, there will certainly be various irreversible processes in the tree and the leaves themselves, but they're not things which are kind of obviously captured by this kind of low quality video. There's no obvious markers which tell us that really this video was played from past to future or from future to past. And in actual fact, I can't even remember whether I flipped the video in the first place. This is kind of getting across this idea that to even prefer to use a direction to talk about things in the world, we seem to need access to things like irreversible processes. If we didn't have such things, it's not useful to talk in terms of a direction of time. Right? When we view this kind of process from left to right, what we see is, a sort of a familiar process, not very familiar, right, hopefully, but it's certainly more familiar than if we were to view this from the other direction, as though the shards of glass were just kind of finely tuned to kind of form a perfectly smooth wine glass over a few seconds. Right, again, we have these very clear intuitions as to which is the right process. And, I don't really need to tell you that this relates in various ways to the second law of thermodynamics, the idea that entropy increases towards the future, not towards the past. This is, a basic time asymmetric law in physics. Right? It's interestingly time asymmetric because it tells us about a different type of process that goes on towards the future than towards the past. And, there are various different ways to understand what entropy is. I usually just describe it as a measure of disorder, but obviously there's countless different ways in which we can define entropy. But the key thing is that given, like Boltzmannian statistical mechanics, what we see is that this is this law is a statistical generalization, right? We certainly expect it to hold for any process we're ever going to see. We expect there to be these different behaviors towards the future than towards the past. But one thing that Boltzmann kind of famously noted is that ultimately there's a simple probabilistic reason why entropy tends to increase. Right? Given that entropy isn't at a maximal, there's many more ways for entropy of any system to increase, so we expect it to increase. And the philosopher Hans Reichenbach, in his very influential book, The Direction of Time, ultimately used this as an actual definition for the direction of time. He didn't ask why entropy increases in the positive direction of time. He just said that the direction of entropy increase just is the direction of positive time. Right? It would be kind of wrong-headed of us to even question whether whether entropy increases in the correct direction of time, or whether things really go in the other direction of time. So we have this first motivation that the kinds of things that make it useful for us to label time as directed are ultimately non-fundamental and statistical in nature. These kind of facts about the world around us. And the second motivation, which is often used for C theories of time, directionless theories of time, is this idea that we have this time reversal invariance holding. That for any process which is allowed, kind of effectively, like we have these 3 billiard balls here moving around a box, if they can go from the state on the left to the state on the right according to the laws, then by the symmetry of the laws, it can also go from the state on the right to the state on the left. Right? So the idea is that any process allowed by the fundamental laws of physics, that there is a time reverse process, given certain kind of assumptions that is also allowed by those laws of physics. And various physicists and philosophers have suggested that, well, if we have these tiny symmetrical basic equations, there seems to be something anti-physical in supposing that time really has a direction. Because if we were just in a world of fundamental particles and we didn't have any aggregate statistical behavior to observe, then we would have no reason for preferring one direction of time over the other. They would both effectively be equal, so adding a direction of time onto that would seem to be kind of superfluous. Now there's a couple of caveats with that. The question of whether the laws of physics are actually time reversal invariant is very fiddly, and it's not so clear that one even needs to appeal to time reversal invariance to defend a directionless picture of time. So it's well known that there are apparent violations of time symmetry in weak interactions, given the assumption of the CPT theorem. And in the case of quantum mechanics, the very form of the time reversal operator is quite complicated, and many people have argued that it's somewhat ad hoc, and there's a motivation to make the theory come out as time reversal invariant, and that's what we use to justify the kinds of time reversal operations that we use. There's this further question that we might never have access to a final theory, a fundamental theory, and in that sense we never will have access to whether the world really is time reversal invariant. This is kind of a big epistemological problem, which suggests that we shouldn't ultimately have our preference for our philosophy of time dependent on some sort of fact that is kind of unknowable. Now secondly, the relationship between time reversal invariance and the direction of time can be kind of pulled out from a couple of different directions, so to speak. So the philosopher Tim Maudlin, he's an advocate for the view that time really does have a preferred direction. He says that his theory, his B theory of time, works perfectly well regardless of whether the laws of physics are time reversal invariant, because, well, it shouldn't have to be the case that the fundamental laws of physics turn out to be time reversal non-invariant to have a preferred direction of time. He thinks that there are all sorts of other reasons why time might just have a direction, and that might give rise, nonetheless, to time reversible dynamics. And I've argued in my own work that the C theory of time doesn't stand or fall with the laws of physics being time reversal invariant. We could imagine non-time reversal invariant laws that still allow us to perfectly well retrodict the past and predict the future and have this kind of two-way nature, and still, in a sense, be compatible with the idea of the C theory. Which takes us to kind of the third motivation, and one that probably most naturally relates to work in time-symmetric quantum mechanics, which is the sense in which the laws of nature do not clearly apply only from past to future. Now, this argument has been put forward in various forms. It was famously put forward by the philosopher Bertrand Russell in a little paper where he tries to argue that physicists shouldn't talk about the law of causality anymore. This was like over 100 years ago, and since then there's been quite a renaissance of the notion of causality in physics. It's become much a much more technically well-defined concept. But Russell was motivated by looking at the form of the classical law of gravitation. He said that when we look at the law of gravitation, what we see is kind of no clear distinction between cause and effect. What we have is a sort of a formula. We have these differential equations which, given the state of the system at one time, can effectively give back the state at any earlier or later time. Right? We have this idea that with deterministic dynamical laws, the state at any one time plus knowledge of the laws will give us a total history, kind of past and future. It doesn't just say how the future depends upon the present based on the dynamical laws, but it also tells us that there's a sense in which, at least in terms of calculation, the past also depends upon the facts about the present according to the laws. And he says that this statement holds throughout physics. Now what we see in quantum mechanics is a more interesting picture, because we're no longer in the case of deterministic theories, and indeterminism turns out to have various ways in which we can have this non-trivial dependence of the present on the future. So in the two-state vector formulation of quantum mechanics, which I'll get to in a little bit more detail if I have the time later in the talk, this is a position which was initially put forward by Aronoff, Bergman and Lebovitz in the 1964 paper, where they were motivated by giving a kind of time symmetrical description of the quantum state that doesn't just depend upon earlier measurements, but in a sense depends upon later measurements. We have this sense that for pre and post selected quantum ensembles, that we can see a kind of dependence of the state upon measurements in the past and in the future. Kind of related to this is the transactional interpretation of Kramer that's been defended in recent years at length by Ruth Kastner. The transactional interpretation, which is a bit like a quantum analog of the Wheeler-Feynman absorber theory of radiation, where we have kind of effectively the state of a system determined by some sort of interaction of a forwards and backwards evolving wave function. And retrocausal interpretations of quantum mechanics, such as those of Olivier Costa de Beauregard and more recently, and again at great length, Hugh Price, open the door to a kind of locality which gets around Bell's theorem by allowing for our choice of measurement settings in a Bell type experiment to have an influence upon the initial state of the particles. Now in each case, what we see with these, I should also say that Ken Wharton in San Jose has also been defending what he calls a Lagrangian-only picture of quantum mechanics, where we give up the idea that quantum mechanics should be kind of formulated as a kind of a forwards-looking theory defined, with states defined only in terms of the past, but in a kind of more Lagrangian sense, that any state, in a sense, depends upon an initial and final specification of boundary conditions. So in a sense, everything is calculated for the history of the universe all at once. Now what we have in common in these views is that they reject the idea of a universe which is somehow fixed at the beginning in terms of the initial conditions and then governed by some only future-directed laws. Right? And there are various ways in which we can think about the metaphysics of this. Right? One, the view that's been sort of attacked, the view which is bound up with the B theory of time, is this idea that reality is really determined only from start to end. But there are two different ways to kind of reject this. Firstly is to think in what I would call a bidirectional way, and think that, well, suppose that there really are these two wave functions evolving, one from past to future and one from future to past, then we can say that reality is in a sense determined by this kind of flow of information in both directions in time. This tends to bring back in various paradoxes associated with the passage of time that comes from the A theory in the first place. A more kind of palatable way to think about this, as someone that defends a C theory in the block universe, is that we can think of these different views as saying that reality is in a sense determined in a way that does not simply fit the unidirectional picture. Right? Reality is in a sense determined all at once, or in a way that allows in principle for some sort of non-trivial dependence of the present upon the future. So both of these views, in a sense, fit with the idea that time is directionless, but the latter of these would fit more naturally with, I think, the block universe view. But we'll kind of come back to that. So a few more things to say about how to understand the C theory of time. I should just check, how am I doing for time?
Yeah, so I was a bit, sorry, I'm confusing myself now because I've set a timer first. So 5 minutes, that would have been, you've got 15 minutes left basically of your 15-minute slot, if that makes sense.
15?
Yeah, 15 minutes left, and then it'll be eating into question time after that.
Okay, I'm probably going to maybe skip over one or two little bits, and I'll just go through this first, okay? So I've presented kind of various ways in which we can think about these different models of time. And I want to say a little bit more about how we should understand this idea of time being directionless. And I'll take a lead from a couple of people who are motivated by the physics of time. So firstly, the astronomer Thomas Gold. So this was in the context of thinking about the time reversal invariance of classical physics. He said that the description of our universe in the opposite sense of time, so that's the direction from future to past, it sounds very strange, but it has no conflict with any laws of physics. Our strange description is not describing another universe, or how this universe might be, but it's actually describing the very same thing. Now, Gold there was, I think, very, very heavily motivated and inspired by Hans Reichenbach's book, The Direction of Time, where Reichenbach said that positive and negative times, so forwards and backwards time, give equivalent descriptions of the world, and it would be meaningless to ask which of those descriptions is true. Right, so the idea that they're both getting at is that we can describe the world from past to future, or from future to past, but these aren't describing two different ways the world could be. Right? There's no fact of whether the world really is going from past to future or from future to past, but these are kind of like it's like describing the contents of a table from left to right or from right to left. They're describing the same reality, just from different perspectives. So Reichenbach kind of had this very broad view of this. He said that ultimately it has no meaning to say that entropy even really goes up, or that its time direction is really positive. And what he's getting at there is the idea that there's no further background arrow of time. It's not some fundamental direction of time that the arrow of entropy is correlated with. We just define the direction of time as the one in which entropy increases, and this has a status of being effectively a convention. Right? It's not expressing something true. It's just expressing kind of a way in which we should describe things for pragmatic reasons. So this kind of gives rise to this idea that the direction of time might not be fundamental. It's not something which is a property of reality. So we're still dealing with a C theory, a directionless theory of time here. But this conventionalist attitude says ultimately there are no time-directed facts, right? This isn't a time-directed universe. And it's not, in any sense, false to describe the world in the unconventional direction from future to past. But it is, for various reasons, just more convenient in our everyday world to describe it from past to future, right? Because of the relationship of causality and entropy, the fact that effects are generally of higher entropy than their causes and so on. This is such a useful way to talk that whenever we're talking about the world around us and we're talking about thermodynamics and so on, we have this clear asymmetry of time. It's just useful to adopt a manner of speaking that suggests that time has a preferred direction. But there's no reason why this should carry over to talking about quantum mechanics or even just classical particle mechanics. I'm just going to skip forward a little bit here. It's a basic idea on this view is that forwards in time descriptions can just be kind of simpler and more natural, they fit with our intuitions about causality and so on, but they ultimately just are equivalent ways of describing the world. Right? So there's a way in which we can deny that time has a fundamental direction whilst accepting that it is useful to describe and model it in a preferred direction. Similar to why it's useful to talk about time as flowing, or we might not think that time really does flow. So it's sometimes argued that quantum mechanics brings in a basic asymmetry of time, a basic arrow of time. One place where this is argued is in Roger Penrose's book, The Emperor's New Mind, and he uses a very kind of simple setup. Right? He has one light source and he has a half-silvered mirror and two detectors. Right? And we have this probabilistic setup that it's a 50-50 chance of a particular photon being detected at detector C or detector D. And he says that what we have in this kind of basic setup is these two kind of conditional probabilities, right? The probability of detecting C given its emission at A is a half, but the probability of its emission at A given its detection at C is not 1/2, it's 1. And this comes out of the idea that, ultimately we think that there's only one possible source. So Penrose says that it's only kind of for calculating probabilities of future states on the basis of past states that quantum mechanics ultimately works. And on this basis, that quantum mechanics cannot be time symmetric. Sorry, I just lost my picture there. There we go. I mean, what's interesting about this kind of argument, we see a similar argument also from the philosopher of physics Frank Arnsenius, with a kind of a similar setup, is that forwards transitional probabilities in quantum mechanics are invariant under a change of initial conditions. So he imagines a second kind of light source here. What he says is you can kind of ultimately flip where the light source is coming from, but still have the same statistics. And we only have this kind of towards the future and not towards the past, in a sense. If we try to retrodict the origin of the light source, he says that we don't have the same sort of invariance of transitional probabilities. And for this reason, quantum mechanics is proto but not retrocausal, and it suggests that time has this objective direction. Well, as is fairly well known, this argument is a much more general argument, and it concerns kind of the nature of indeterminism and probabilities, that they can only effectively kind of go one way in time, which we've kind of set up our kind of statistics. And we've seen that this kind of argument has also been applied outside the context of quantum mechanics by people like Watanabe and Elliott Sober. The idea is that if we have a law of nature which is probabilistic and time translation invariant, it must also be kind of effectively directed in time. So I'm just having a bit of a problem with the computer at this end here. So the motivation that Penrose had here is that ultimately we have this further knowledge in the background, right? And this kind of gives the game away. He says it's virtually certain that if one of these photocells registers that the photon came from the lamp, not the laboratory wall, right? Implying that kind of the bottom of this diagram will be a wall and not a possible emitter of light. But as the philosopher Craig Callender points out, if you're generally concerned with time reversal invariance of quantum mechanics here, Penrose should treat kind of the emitter as a receiver and vice versa, right? And in the time reverse case, if we ultimately conditionalize on kind of an emission of a light, of a photon from C, then we can kind of get back effectively, you know, 50-50 probability of detection at A and B, but we have to kind of ultimately do this by using a kind of a post-selected ensemble of systems. We throw away certain information about the past. We only deal with cases where a particle ended up at C. We don't have information about its origin. In that case, we can kind of apply the same sort of transitional probabilities towards the past. And it's this idea of post-selection, of selecting our ensembles in a symmetrical way, which is ultimately kind of the main motivation of the Aronov approach of time-symmetric quantum mechanics, which we can look at in a bit more detail now. So to pick up on where we are so far, so we're looking at this difference between like directed and directionless time. On the kind of directed view, we can have this idea of causality as being fundamentally one way, and that states only depend upon earlier and not later states. Whereas on the C-theoretic picture, we can have, you know, in principle, a less clear-cut notion of causality and a kind of a possible dependence upon future and past states. So when introducing his general approach in this, Aronov talks about the sense in which indeterminism brings in kind of new possibilities for time symmetry. That if we just deal with kind of classical physics and deterministic systems, we have a very kind of boring sense of time symmetry, which we kind of looked at earlier, which is the idea that, you know, Laplace's demon in theory can be given all the information about the position and momentum of every particle in the world and be given the precise dynamical laws, and therefore can sort of figure out how things were in the past and how things were in the future. And there's this kind of trivial sense of symmetry here, in that history, in the history of the universe, in this classical picture is determined on the orthodox picture by initial state plus the dynamics, but it's equivalently also determined in a similar sense by any given final state and the dynamics. What we get with indeterminism is the possibility of a non-trivial sense of the present depending upon the future. The idea that initial and final conditions can provide more information about the state at some intermediate time than simply the initial conditions. So the approach of Aronov and his many collaborators on this is to think of pre-selected ensembles as being kind of the standard way in which quantum mechanics is understood, but the fundamental notion that we should be dealing with is pre- and post-selected ensemble. Right? We should select our statistics of runs of an experiment in terms of a given kind of initial state and a given selected final state. We can do this effectively by throwing away data about systems that happened to end up in effectively the wrong state. Once we have this kind of sub-ensemble of pre- and post-selected systems, and we can have a sense in which the state at any time has a non-trivial dependence, kind of at least in terms of its kind of calculation upon its past and future measurements. So they're very clear to put forward the two-state vector formulas, not as an interpretation of quantum mechanics, but just a different way to formulate standard quantum mechanics. It's kind of playing with statistics, and it's given a new way of formalizing things to effectively allow us to think in a more time-symmetrical way. Right? It gets rid of certain implicit time asymmetries in how we ordinarily represent quantum mechanics. But you know, one of the ideas here is that, well, we always write down quantum states in terms of past measurement outcomes because that's the most we know. But it's not to say that that is everything there is, kind of in terms of the facts about that state. There might be dependence of the state on facts about the future we just don't have access to, so conventionally we don't write those down. The only way we can kind of effectively have the surrogate for this is to have a pre- and post-selected ensemble, and then we can talk about kind of earlier states of that system as effectively depending, in a sense, upon a later measurement outcome. Now, there are various asymmetries in the world, which mean that there are very various differences between this kind of forwards and backwards evolving wave functions that they talk about, right? We can ordinarily just prepare a system in some given state, but there's no act that we can really do to kind of post-pair a system to make sure it kind of ends up in a particular outcome, unless we have a, you know, kind of effectively probability 1 of some outcome given this initial state. So pre and post selected ensembles are in a sense a kind of an artifact, or a statistical artifact, which involve discarding certain actual runs of the experiment that just didn't come out to be in the post-selected state. Now, what's important to think about here is what this kind of way of thinking about quantum mechanics says about the world. Right? So the primary benefits that are put forward by the likes of Aronov on this are ultimately pragmatic, right? They help us to see or explain or predict certain kind of quantum effects. Right? So one is weak values, which I'm not going to get into, partly because I don't think I have the time to do so. They seem that the two-state vector formulas became particularly useful after kind of the introduction of weak measurement and the discovery of weak values and things like that. It's very difficult to understand these effects, I say, in the framework of standard quantum mechanics. So this gives us the idea that allowing us to think about a kind of a non-trivial dependence on the future effectively kind of acts as a useful heuristic to kind of open the doors to thinking about certain kind of possible effects, certain things that we can predict, certain things that we can, in theory, explain. The standard way in which, you know, these wave functions are normally talked about is in terms of propagating forwards and propagating backwards in time, which, you know, that's kind of problematic. What does propagating really mean? It sounds a bit like this kind of a theoretic way of time evolving, but maybe we can understand it in a more restricted sense, or a more kind of fictional way, that we can use this language of forwards and backwards wave functions as a useful heuristic for making certain predictions, which maybe are more difficult to come by using standard formulations of quantum mechanics. Likewise, Aronov, Peskin, and Tolleson here say that, well, in orthodox quantum mechanics, it's standardly assumed that only the results of measurements in the past exist. Sort of again suggesting the idea that, you know, standard quantum mechanics is sort of stuck in a sense in which the future doesn't yet exist, that the future is open. Again, kind of corresponding a bit to like the A theory of time, and their view kind of commits us to more of a block universe picture. Can I check again on time? Because I feel like I'm probably around the point at which I should start wrapping things up.
Yeah, that's correct, yeah.
Okay, cool. Okay, so just to kind of end up, I'll just have a quick word about retrocausality, which is another interesting thing which is sort of opened up by the C-theoretic way of thinking. So, you know, with Bell's theorem, like, famously, it's traditionally talked about as a proof that any realist theory of quantum mechanics has to be non-local. Right? There's these assumptions of realism that, you know, there are facts about the world that would have been the case even if we hadn't measured them. Locality, that we don't have faster than light influences, and agent freedom, that, you know, experimenters really are free when they make choices about their measurement settings. And one thing that Bell's theorem shows us is that there's a kind of an incompatibility of the three of these. Right? So if we assume realism and agent freedom, we end up with non-locality. If we want to assume locality, we have to apparently give up either realism or agent freedom. And Bell famously thought that, well, perhaps you could give up agent freedom and end up in a kind of a super deterministic. Yeah, so the super determinist picture would be the idea that, you know, there are already, in a sense, facts about how the particular experiments are going to be measured independently of our choices about how to measure them and so on, which Bell thought was problematic. In a letter to Hugh Price, he said that he can't really think about kind of ways to avoid Bell's theorem in a sense without lapsing quickly into fatalism, this idea of ultimately the future being determined independently of our decisions. But what he says is that he struggles to have this idea of backwards causation, which wouldn't entail fatalism. And more recent work in foundations of quantum mechanics has certainly made rhetorical causality seem a lot more palatable, partly because rhetorical causality does not explicitly give up in any sense agent freedom, right? The idea behind retrocausal models put forward by people like Hugh Price is that what's central is that the experiment does have the freedom of how to measure systems. It's just that their choice can effectively have some backwards directed influence on the initial state of the particles, and through this kind of zigzag we end up with a kind of a seemingly local resolution of quantum mechanics. So whereas Bell kind of takes for granted that states and systems are independent of future measurements, Hugh Price and others have heavily criticized this assumption. Right? Going back as far as Costa de Beauregard, he said that, you know, in the case of EPR, you know, kind of the predecessor to Bell's theorem in a sense, he said that Einstein is right in seeing this problem of non-locality, but only under the assumption that advanced actions, kind of effectively backwards in time influence, are excluded. What motivates Price is this idea that in microphysics, it's not so clear that we have a clear intuition that things should depend upon the past and not the future because of things like time symmetry, right? Going back to our initial thoughts, the reasons why we think that the present depends upon the past is largely boiled down to facts about thermodynamics, facts about statistics. But we end up with just, you know, particle mechanics. It's not so clear that we should have a preferred direction of causality. A preferred direction is sort of putting something extraneous into the picture. And if we relax this, we allow in theory, the possibility, the option of having some sort of retrocausal influence of our measurement settings on the earlier state of the system. And that offers a potential way around Bell's theorem. But it's crucial here that experimenters are still free to choose their settings, and it's in this sense that we have retrocausality. Okay, so I'm just going to sum up here, and apologies for running a little bit over. So some final thoughts. Right, I've talked a lot about the metaphysics of time and interpretation of quantum mechanics. We can think about how these things relate, and I have just sort of a few broad lessons. So the B theory of time's directed block universe seems to rule out the effectiveness of the future of quantum past. We can't appeal to things in the future to explain the present. Right? It seems to rely on this idea of a force-directed picture of things like Bell non-locality and weak values. In a sense, it kind of gives this restriction of the kinds of explanation that we can give in physics. Now, we've seen how time-symmetric theories of quantum mechanics, like the two-state vector formalism, can be read in kind of a thicker metaphysical, almost a-theoretic way of forwards and backwards evolving wave functions that potentially entail paradoxes. But I think that a more natural way to interpret these things is that the two wave functions are kind of calculative devices that kind of give rise to this idea of a world which is just determined, in a sense, equally by facts about the past and the future. Now, are these reasons to adopt the C theory? Well, it's not clear why we would need the extra heavier metaphysics of a fundamental direction of time in the first place. Right? Why not just see what the right interpretations of quantum mechanics can give us without having to input this background direction of time? But also the C theory seems to allow us to kind of have access to a wider range of options for understanding or explaining quantum mechanics, such as time-symmetrical or retrocausal approaches. And it's not clear why these should be ruled out just kind of a priori. So kind of the final suggestion ultimately is one reason to go to the C theory is ultimately just to lose the explanatory straitjacket. And thanks again for listening, and yeah, I hope that there's some kind of questions, if not now, then in the discussion later.
Yeah, thanks very much, Matt. Yeah, we do have time for questions. I'm sure there will be many questions. Okay, very good. Jared, I think.
Thanks, Matt. That was a great talk. Just a question. Hugh Price has been a champion of the perspectival view of causation, and I think it wouldn't be a big stretch to think of time as perspectival as well. What's your view that time is simply a concept that agents use to order their experience and is not in fact in the world at all?
Yeah, so this is a view that I'm really sympathetic to. I mean, I think that, so I defended a position which is very closely related to perspectivalism, which I call conventionalism, and it's the idea that, you know, we shouldn't have it as an aim to simply get rid of reference to the direction of time in physics or in everyday discourse, but in certain situations it's useful to talk about things in a preferred direction, and one of the reasons is so that, well, we do have certain perspective on time as agents, right? If we want to, say, construct a causal model of something, we have to deal with whether something is a cause or an effect in order to fix all the other errors in the model. One thing that we should never throw away is the idea that, well, we take our freedom as an agent to be something which plays a constituted role there. I mean, that is certainly very, very much in line with the perspectival view of causality. And I think that there are various reasons why we should think that the direction of time, earlier to later, should ultimately, for the most part, match our notion of cause and effect. Or we have a useful kind of distinction between cause and effect. For the most part, I think that should correspond to, fit with our notions of earlier and later. But yeah, ultimately, I think what justifies the use of such language is going to be facts about us, facts about our memory and how we interact with the world, and even facts about how we think we experience time. So yeah, the very short answer is it's very closely related to this perspectival notion, but it's something I can probably say a bit more at length on another occasion.
Charles.
Hi Matt, thank you, that was really fascinating. I hope you'll forgive a question for completely labelling this kind of thing. You made a comment that if we lived in a world of fundamental particles, we wouldn't see these statistical properties of time, and time laws would be asymmetric. But we kind of do live in a world built purely out of fundamental particles, and yet we do see these statistical properties emerging. So I guess you then talked about time being a convenience, because it's useful to explain, or just to talk about time as if it's going in the direction that entropy goes in. But the question then is, well, why does entropy go in that direction then? And are we, if we're just saying that time is convenient, it seems like we're asking for time to somehow mean more than just a parameter that allows us to make predictions about the world. Is that just asking too much of our definition? Isn't that all we need?
Yeah, so on the first point, so the idea is, well, if we were only ever, I mean, it's hard, obviously, in this way of thinking, when we're saying that if we were in a world of fundamental particles, obviously then we're putting ourselves in there, so it's already breaking the kind of the picture. But if you were to just sort of observe, a complicated video in your particle interactions, and you didn't have the ability to see any macroscopic patterns or anything like that, kind of how, I guess, Laplace's demon would be, traditionally presented, then there would be nothing gained from putting in a direction, saying that really this is a world that goes from one state to another, right? There's nothing that's kind of motivating that, and there's nothing that's going to help to explain. Now, yeah, certainly we're in a world where we do have emergent time asymmetries, right? We can't get away from that. And I think ultimately what that should do is to ground what we call the future and what we call the past. It's not evidence that there is an underlying directionality of time, which would be there even if the world was just a sea of particles with no macroscopic patterns, right? So can you sort of repeat the second part of the question, because I think I might have missed one key detail.
So I guess the second part was saying that if you accept that properties like time-dependent asymmetric things like entropy can emerge, and you say, right, I call that direction the convenient thing to talk about as forwards, but it's just a convention. Isn't that the answer? Why do we need more than that? Isn't that what we mean by asking where does time go?
Yeah, I mean, this is ultimately really synthetic too. So we could ask, one thing that the likes of, say, Boltzmann kind of certainly pointed in this direction, and Hans Reichenbach kind of sort of defined things in this way, that there is nothing more, in a sense, to the direction of time than the direction in which the entropy of systems increases. Right? That's just a definition. Right? That's not to say that really entropy only goes up, because to say really entropy goes up is to kind of invoke this idea of a further direction of time relative to which entropy increases. So for Reichenbach and this definitional approach, it's sort of almost like a truism that entropy increases, right? Because you're defining the positive direction of time in terms of entropy increase. Right? You could imagine there being some hypothetical scenario where you have some very isolated system which seems to evolve anti-thermodynamically relative to the rest of the universe, and then you could say, well, the entropy for that system is going backwards, but it's only going backwards relative to kind of the direction of time defined in terms of the other thermal systems. Now, the view I prefer is kind of Reichenbach's ultimately, that we shouldn't even ask the question of whether really entropy is going up or down, because it doesn't really play, this further background direction of time doesn't seem to really play any role. So it shouldn't be there in our basic ontology of time or anything like that. We should think ultimately this is an emergent feature of the world. The question, does it also emerge independently in quantum mechanics? I don't think it does. The one that we're usually dealing with is the one that comes out of thermodynamics. When we're dealing with something like classical or quantum mechanics, there's no need to impose this further notion of the direction of time. Does that kind of address your question?
I think it does. Thank you very much.
Okay, I think it's good to keep going with questions and kind of delay the coffee break. So maybe we have questions from this side of the room, and then I'll get to you guys. Okay.
Thank you for that really soothing presentation. You said that the argument that phenomena do seem to happen and that would be impossible to simulate is a weak argument. Well, it seems pretty strong to me, but I'm very young and inexperienced, so I'm sure you could enlighten us with a short logical refutation of that argument. Thank you.
So, sorry, I think the mic distorted quite a bit at my end there. So what I thought you were saying was that the argument from experience is not a weak argument, but it's a stronger argument than I suggest. Is that it?
Well, I mean, since you seem to consider that it's a weak argument, I would like to ask you for a short logical refutation of that argument. So the argument is not only that things seem to happen, but also that the fact that they seem to happen would be impossible to simulate.
Yeah, and so I mean, this is an ongoing debate, say, in the question of whether time really flows or something like that, right? That many physicists have suggested that we do need some non-trivial explanation of why time seems to flow if we prefer a model which doesn't have a flow of time sort of put in there. I don't think, so one of the reasons why arguments from experience, I think, are not that great is that people have a great tendency to sort of disagree with what their experience does actually suggest. Right? So one debate between static and theorists of time has been whether the static theorists take time seriously. And there's this kind of great philosophy paper from the 50s by this guy called D.C. Williams, who said that the very kind of nature of this dialectic is a bit kind of stacked. It suggests that there's this special appearance of time that we have that only the dynamic time theorists are taking seriously, and that the B theorists, the block universe theorists, are trying to kind of get rid of. But conversely, he points out that defenders of the static view, a lot of the motivation for that is when we think about what it really means for there to be a preferred noun, for it to kind of move from early to late and so on, we end up with this kind of paradoxical picture. There are these kind of famous paradoxical arguments about the passage of time. And what they suggest is that no, the way time appears to us is not as something paradoxical, but something that ultimately fits with what we normally represent using a static view of time. When we're representing it as static, as four-dimensional, it's not saying that in such a world time appears to be kind of static or still like that, but our various notions of seeing motion and experiencing transience and so on is fully predicted on that model, on the block universe model. So in a sense, experience acts as it just kind of gives us a stalemate, because we have a disagreement between the two parties as to whether their model is actually capturing the experience or not. The B theorists, the block universe theorists, will say that their model perfectly well does capture our experience of time. So that there's a kind of there tends to be a bit of a stalemate, which is why I say that it's a bit of a weak argument. The dialectic of the argument is it's become rather frustrated over the decades.
Okay, Jake, and did you have a question, Chris? No. Yeah. And Pauli, and then I think we have to stop there because it could keep going forever. But yeah, Jake, go for it.
Thanks, Matt. I really think that philosophers and physicists should talk more to each other, so thank you for putting up with us. In the research group I work in Vienna, there is an adage which I think we sometimes throw at each other, which is that time isn't real, clocks are. And I wonder what you would make of sort of this small adage. I think what we are trying to get to, if I can just give some context, is something like, for example, if you think about thermodynamics, temperature is not real in some sense. Heat exchange is. Like, heat exchange is something which is experimentally real. So in this sense, like, temperature is less ontologically meaningful than heat exchange, for example. You could say that entropy is more meaningful than time. I think that's where we're coming from. And how does that square with your thinking on the matter? Thanks.
Yeah, it's a really good question. I mean, I'm certainly sympathetic to this idea that we don't want to enshrine kind of certain notions that are useful to put into the way we describe equations, into features of the world, right? Things like temperature and so on. So in the case of time, I mean, there's good reason to think that there's not necessarily this thing fundamentally called time. It's just a useful way, a useful shorthand for thinking about like the relative changes of systems that we can compare with each other, which kind of fits with our notions of how clocks work and how clocks are reliable and so on. One of the things which motivates me from the philosophy side when I'm talking about time is, there is a whole way, a whole wealth of ways in which we do talk about time, and one thing that we're trying to do is to work out what's conceptually necessary for time to exist. So that has been something that has been central to the debate in the last 100 years. So A and B theorists have historically argued whether the flow of time is something conceptually necessary for time to be real. And now I'm more in a discussion, a debate with other block universe theorists as to whether the direction of time is something which is necessary for time to be real. And I have this view that, no, pragmatically we can say that time is real in a situation where we don't have a preferred direction. We just have this sense that we have things going on which seem to depend upon each other in certain law-like ways, so it's useful to have these kind of dynamical equations relating to them. So in a sense, when I'm talking about time, I do have a notion of a more complicated picture where time isn't necessarily a central term, but when we're using the concept time, I'm thinking about, well, what's the least structure we need in order to say that that thing that I'm talking about is time and not something which is non-temporal. So there's kind of an issue, I guess, of conceptual analysis and semantics and so on in all of this, but it's not seeking to undercut the view of people that say, we don't really, clocks don't really measure time. In the sense they don't measure time, they define time, and I'm perfectly, on board with that idea.
Okay, Christoph. Yeah.
Thank you for this very interesting and excellent talk. I have one question. In last part you talked about Hugh Price and I guess the difference between microscopic systems where you actually struggle to define the order of time. You may have things like rate of causality, whereas macroscopic systems where you do have entropy and you can get the direction. Now, this is suggestive of some form of a Heisenberg cut, maybe, but there's another Heisenberg cut where you would say, oh, this is kind of the size of systems when things like interference and particles being in two positions disappear. Do you see any philosophical relation to link those two levels of a Heisenberg cut, or are they totally separate questions?
I think I need you to repeat the question. I just had someone just moved very loud.
Sure, no problem. My understanding was that from Hugh Price's point, you have in a microscopic system, you do have some form of visibility of time, you do have possibly retrocausality, things like this, whereas in macroscopic systems, you have the law of entropy, which wouldn't necessarily allow that. So this, for me, would be some form of making a cut between a microscopic and a larger system, like a Heisenberg cut.
Right.
Then the normal Heisenberg cut would be something like when you say, oh, systems are so big that you don't see a superposition of two different position of objects, and you don't have interference phenomena, which are slightly different questions independent of time. Do you see any philosophical basis between linking these two Heisenberg cuts?
Yeah, that's a good question. It's not something I thought sufficiently enough to give a short answer. I mean, certainly on the former, I mean, it seems, obviously reasonable to me to think that we can have a notion of retrocausality in a quantum case which doesn't correspond to anything kind of classically retrocausal that we could do anything with, and that is fine. How to relate it to the second picture, I've not really thought about enough detail to kind of give you any well-informed answer.
Thank you. So, yeah.
Also, once again, thanks for the very interesting talk. So my question is regarding, let's say, in how far theory B and C are compatible with like a non-superdeterministic view of the world, because you touched shortly about it, but basically the only arguments I thought of like that make theory B and C compatible with non-superdeterministic worldviews are basically the post and pre-selection or retrocausality, which in my opinion like are way too powerful mechanisms, and one would have to come up with like ways how to restrict them in order to not kind of like cause their own problems. So are there any ways to convince somebody of theory B and C without slipping superdeterminism through the back door?
Yeah, it's a really good question. I mean, I've always been tempted by any epistemic accounts of the way it functions to try to see an analogy between quantum mechanics and like statistical mechanics, but then obviously things like the BBR theorem make that really very difficult to deal with without making recourse to something like retrocausality. I mean, I'm more sympathetic to retrocausality than I feel I used to be, because, I mean, one of the virtues of like the C-theoretic picture is just the idea that we're not just casually excluding the possibility that things depend on the future. Now, if you're dealing with a system which is fundamentally indeterministic, then it seems quite reasonable to say there are non-trivial ways in which facts about the present depend on facts about the future. We just don't know what those facts are from our perspective. In that sense, I mean, you can understand that in a retrocausal way, you can understand that in a kind of a two-state vector type way. I mean, the way I see things is that you're left with those as genuine possibilities if you're a C theorist. Now, what's the alternative? To go for some sort of like future-directed collapse model or something like that? I mean, I don't see why that's necessarily a preferable way of understanding quantum mechanics. I mean, one of the main reasons it's been defended is that it seems to, in a sense, correspond to the way in which we understand measurement outcomes and so on. I can kind of see why people think that the standard kind of collapse approach fits quite naturally with the idea of a B-theoretic universe, because it seems to suggest that there is, what the state of the world is determined by what's going on now and not in the future. But I'm always kind of left with this idea that, well, there are good reasons to think that there are going to be facts about the future. I mean, we just don't know what they are, and that's ultimately a shortcoming in our knowledge. And the way in which we write down states of systems is in terms of what our knowledge of the system really is. So, I don't know, I just find it quite appealing to make use of approaches like the Aronoff approach. I don't necessarily think it's a heavy kind of metaphysical picture that it gives you, but it just sort of opens up the door to there being dependencies of nature which go beyond what we can actually have necessarily access to. So it's not really an answer to your question. I'm just trying to deflate the radical sounding natures of things like retrocausality and the two-state vector formalism. Part of what I want to do with this work is to kind of make them seem a little bit more appealing to people that don't want to believe in crazy metaphysical views.
Okay, so with that, I think we should give Matt a very warm thank you.